Good afternoon, everyone. I'm Michelle Saner. Today, we are going to be talking about molecular geometry. So by the end of this video, I hope that you'll be able to predict the 3D structure of a molecule using its molecular formula and its Lewis structure to identify the number of bonding regions, non-bonding regions, and be able to look up on a table what geometry it might have. Later on in class, we're going to be learning how to predict that without a table, but for today, we're just going to be learning how to identify bonding regions and non-bonding regions. So for today, we should talk about that the properties of molecules are not only determined by the number and the types of atoms, but in the three-dimensional ways that they are bonded together to form that molecule. The three-dimensional space that they occupy and the shape that they form tell us a little bit more about a molecule's properties and how it's going to behave. Things like boiling point, melting point, adhesion, cohesion, surface tension, lots of different components. So remember that, we move from, for example, a chemical formula H2O, we move to a Lewis structure of H2O, and that allows us to go from kind of like 1 to 2 dimensions, but this water is not flat. What does this actually look like in three-dimensional space? How is this molecule put together? So we're going to start to use Lewis structures to allow us to predict what's going to happen in 3 dimensions with each molecule. So why is this important? As I was saying before, this three-dimensional arrangement tells us a little bit about a molecule's overall polarity. And we learned last time about bond dipoles, the idea that atoms and therefore molecules have areas of greater electron density around them that makes something polar, or maybe they have equal sharing of electrons and so their electron density is equal throughout. In both of those cases, those molecules will behave differently in comparison to other molecules. So for example, we can have a molecule that has a combination of nonpolar covalent bonds, polar covalent bonds, and even some ionic bonds, but the overall molecule could be polar covalent or nonpolar covalent or even ionic. So now we're looking a little bit bigger than we have in the past where we compared the bond of one type of atom to another. Now we're looking at polyatomic molecules with many different atoms that have many different characteristics. And how do we account for all of those? And this is where geometry comes in. So remember that molecular polarity, right? The idea that a molecule may have uneven distribution of charge. A molecular polarity is uneven distribution of charge, that is to say electrons in a molecule. And so the result is that you will have a molecule with one side or end that is slightly positive or one side or end that is slightly negative. And this causes various interactions to occur on either the positive or negative side. So shape, three-dimensional shape of molecules determine many of its properties. So molecules' polarity, its areas of high electron density and low electron density, determine many of its properties such as boiling and melting point, whether it's hydrophobic and it doesn't interact with water, or hydrophilic and it does interact with water, surface tension, cohesion, adhesion, all of these are properties that can be determined by a molecule's overall polarity. So when we move from Lewis structures into 3 dimensions, we use the Lewis structure and combine it with something called the Vesper theory. So I know that this is really pronounced Vesper, but as chemists, we tend to just call it Vesper theory. And this is an acronym for a theory. Vesper stands for valence shell electron pair repulsion theory. And it basically says that when you have electrons that are negatively charged, they will repel away from other pairs of electrons that are also negatively charged. And this makes sense. So the Vesper theory states that repulsion between sets or pairs of electrons cause them to be as far oriented, as far away as possible in a molecule. And so they move in such a way to maximize their distance from other electron pairs. So they tend to spread out as far as they can without bumping into another set of electron pairs. The basis of this theory is that this idea that negative charges repel one another and positive and negative charges, as you know, attract one another. Opposite charges attract, but same charges, in this case 2 negative charges, will be repulsive to one another. So like anything, using the Vesper theory, requires us to follow a procedure. So we have a little procedure for how to take things from a chemical formula into the two-dimensional Lewis structure and then up into the third dimension with the actual geometry. So here are the steps to make this happen. First, you want to draw the Lewis structure. So take the chemical formula and convert it into a two-dimensional Lewis structure. And this will allow us to look at the central atom. And that central atom is going to be connected to bonds. It's going to be connected to possibly to pairs, lone pairs of electrons. So count up the number of areas of electron density. This is anything that's in a single, double, or triple bonds. It just counts as one area of electron density. You'll also want to count up the number of areas of electron density due to non-bonding electron pairs. Another word of that for that is lone pairs. So these are those little pairs of electrons on top, bottom, left, or right of the central atom. And that's a different type of electron density. So we look at the number of electron bonding electron density areas and the number of lone pair electron density areas. And once we have those two values, we'll be able to make some predictions about the shape. And for now, we're going to use this chart from our book. It's from Holt 2006's chemistry book, textbook. And so this is the atoms bonded to the central atom. We are looking for areas of lone pairs of electrons here and number of bonds here, number of bonding regions. And here we have number of lone pairs. So I would like to do a couple examples with you, show you how to use this, this chart. Later on, we'll learn how to do predict geometry without the chart, but for now, we're just going to use the chart to start to work at the third dimension. So let's start with water. You should be able to draw the Lewis structure for water. The central atom, oxygen, has two regions of electron density that participate in bonds. So oxygen, you could say, has two bonding regions. Two of its sides are touching bonds, and two lone pair electron regions. So I want to stop sharing for a second and show you what this looks like in 3 dimensions. So let's say I have this water molecule, and this little piece of metal is going to represent my central atom. I'm going to put a couple of hydrogens on it. We'll use blue. And then I'm going to use black to represent those electrons. And what you'll see happens is that all 3 of these regions, the bonding regions, these 2 blue represents bonds to hydrogen, these 2 black represent just lone electron pairs in this example. What you'll notice is that they want to push each other as far away as possible. So being linear isn't necessarily as far away as you can get. The way to maximize the angle in 3 dimensions is to actually be a little bit bent like this. So these 2 lone electron pairs push the bond with hydrogen out a little bit, out away from a 2D plane. And when you're able to maximize the angle between all 4 of those different electron regions, you end up with a shape, and you can imagine if I took off the bonding electron regions, because you won't be able to see them, they're just electrons, you end up with a shape that's overall bent. So water is a bent molecule. Now we'll look at the table and we'll confirm that that is indeed the case for water. So we saw that water had 2 regions where the atom was next to a bond, and 2 regions where that central atom, oxygen, was next to lone pair of electrons. So 2 bonding regions, 2 lone pair regions corresponds to a bent shape. And our example, our fantastic example, is right there, water. So you may often see the Lewis structure drawn like this. And that's another way for us chemists to understand that we are talking about something that is in 3 dimensions, a bent shape, such as this. So let's do another example. Predict the geometry of NH3. So we have 1 nitrogen atom in the center, bonded to 3 hydrogen atoms. The number of valence electrons for nitrogen is 5. 1, 2, 3, 4, 5. Each hydrogen has 1. When I connect it and clean it up, I end up with a molecule that looks like this. Nitrogen in the center, bonded to 3 hydrogens. And I want to stop sharing for a second because I'd like to show you what this looks like in 3 dimensions. But let's count up our regions of bonding and our regions of non-bonding electrons. So nitrogen has 1 lone pair region right here, one set of lone pair electrons touching the central atom, and 3 bonding regions. So 1 lone pair and 3 bonding regions. All right, let's see what this looks like. So once again, I have 3 hydrogen atoms. I'm going to represent them in blue. And I have a lone pair of electrons. Now this would be perfectly flat if there were no other electrons present. But this lone pair of electrons here at the top forces my 3 hydrogen atoms slightly downward. And again, we're trying to maximize the distance on the angle here. So we have to think in 3 dimensions. So this molecule, NH3, with its lone pair of electrons here, and I'll remove them so we can kind of see, I'll move those invisible electrons so that all we're left with is the atom. You can see that I end up with kind of like a little bit of a pyramid shape, a 3-sided pyramid, slightly bent away out of the plane. So you can see these 3 hydrogens bending down out of the plane of that pyramid. So going back to our example, let's confirm that to be true on our table. So we're looking for something with 1 lone pair region and 3 bonding regions. So I check the chart. 3 bonding regions and 1 bonding regions is known as a trigonal pyramidal. Okay, so the official name for this is trigonal pyramidal. You've got a central atom in the center, some other atom coming out front, side, and then a little bit in the back, like a little tiny pyramid, 3-sided pyramid. So this is a trigonal pyramidal molecule. All right, let's try one more example. And then tomorrow we'll get in the lab and we'll actually start playing around with simulations for these. Carbon, the central atom, bonded to 4 chlorines. And when you draw out the Lewis structure, you end up with chlorine having 6 electrons and one bond, 3 pairs of electrons and 1 bond, 3 pairs of electrons and 1 bond. But again, we are only looking at the central atom. So what happens to the central atom, carbon? Carbon has 4 bonding regions. Another way of thinking of that is it has 4 sides touching bonds, 4 bonding regions of electron density, and 0 lone pair regions. So all of carbon's electrons are already participating in bonds. All right, I think I will try to make this little carbon, and I'm going to stop sharing with you so that I can show you here on the screen. So imagine that my central atom carbon is at the center here, and I'm using these black tubes to represent the bonds that it's forming with chlorine. So because I have 4 different bonding regions, I'm not going to be able to be completely flat in a plane of 3. Instead, much like the last 2 examples, I'm going to have something that forces this planar configuration a little bit down, maximizing the bond angle between this atom and this atom, this atom and this atom, this atom and this atom, and all the atoms in there. And so all of these bond angles are the same. They're the farthest possible distance they can get away from one another, because again, the Vesper theory is rooted in the fact that electrons repel from one another. So they spread out in such a way that they can get as far away from the other electrons as possible. And when you have a shape like this, 4 different atoms bonded to a central atom, this shape is called tetrahedral. So we go back to our chart just to confirm our findings. 4 bonding regions and 0 non-bonding regions corresponds to a molecule that is tetrahedral. So we've seen bent today, we've seen tetrahedral, we've seen trigonal pyramidal. There are several other geometries you can have. And what you're going to do is just compare how many atoms or how many bonds your central atom is attached to, and how many lone pairs of electrons your central atom is attached to. And it will tell you a little bit about the geometry. Now, the next time we meet, we're going to go into the lab and start running some simulations on different molecules. And you'll be able to see firsthand how adding and removing electrons forces those bonds with other molecules away from each other and starts to create different angles for the bonds and different geometries for the overall molecule. So I hope you're doing well and that you have a great day, and I'll see you next time.